Hi, in this chapter we're going to take a look at inference about the difference between two means. So, like in this first case, we're going to look at the speed before and after an increase in gas price. We'll look at some other ones with other differences between men and women and those kinds of things. So it's an interesting kind of, excuse me, inference to look at. Do the samples indicate something significant? And there's two types. There's the independent samples, which is what we'll be looking at in these first set of problems, and then the last problem will be the difference between a matched pairs experiment, which I'll talk about later. But with this independent samples, one of the things we do is what's called an F-test. And an F-test is used to test two variances to decide whether to use an equal variance t-test and equal variance estimator of u. So again, it'll determine whether to use equal and unequal, and we'll do mostly problems that are equal, but there will be one unequal, so you can see how that works. So to start out with, we are going to find out the average of x bar 1. And in this case, x bar 1 is going to be the before. Maybe I should talk about the problem a little bit here. It's 12.2 on page 202 of your textbook. It says, how do drivers react to sudden large increases in the price of gasoline? And so what happened was a statistician recorded the speeds of cars as they passed a large service station. He recorded the speeds in the same location after the service station sign showed the price of gasoline had gone up by 15 cents. And the point we're trying to figure out is, can we conclude that the speeds differ? So we're going to start by calculating the sample mean in cell E10. So we go equal, and it's going to be average, and we're just going to select A2 to A13, hit enter, and we come up with 33.333. And now we want to do x bar 2, which is the after. So again, equal, average. I can just double click here, and then I can drag and select the range. And in that case, we get 31.5. So now we want to go on to calculate the sample variance down below, but while we're up here, I'll just plug in, we've got 12 variables, 12 cars were sampled, the speed of which, and now we can go in and figure out the variance. So equal VAR, and what we're going to take here is the variance.s, that estimates variance based on a sample, ignores logical values, test and samples. So I'm going to double click here, and then I'm going to select the before, and that should give us 20.24242. And let's do the same with the after. Double click here, select the cells we want, and there we should have 12.09091. So to do the F-test, the easiest thing to do right now is just to go and divide S sub 1 squared divided by S sub 2 squared. So equal 20.24242 divided by 12.09091, which gives us an F of 1674185. And in this case, with that F-test, we're also going to look at what it would mean to take the F for the confidence level we want and the degrees of freedom, and then look to see what rejection range that creates, and then look to see whether this 1.67 falls in the rejection range or not. So let's go ahead and calculate this. Equals F, and it's this F dot INV returns the inverse. So I'm just going to double click here, and then it tells me put in the probability, which is the 0.025, put the comma to separate the different parameters, the degrees of freedom. In the first one is going to be that N1 12 minus 1. We'll just type in the 11, and it's going to be the same for degrees of freedom 2. Close the parentheses, and it gives us 0.2879. So that's on the lower end, and then we'll do it again with the upper. In this case, the probability is 1 minus the 0.025, and then we've still got the same 11 degrees of freedom. And with that, we calculate 3.4737. So now you can see over here, and I'll move over so you can see this whole thing. The rejection region would be an F less than the 0.2879 or an F greater than the 3473. Since we have an F that is calculated at this 1.674185, it's not in the rejection region, so we will use the equal variances test statistic. So the first thing that we're going to do to help work through this is use this formula for the S sub p squared. It's what's known as a pooled variance estimator, and we're going to need that down below here to calculate the t-test. So let's just calculate this first, and what I've done is I'm going to break it out, do the numerator, then the denominator, and then numerator divided by denominator to give us the S sub p squared. It makes the formula a little easier to follow and less likely to make a mistake. So let's scroll this up just a little bit. So it's going to be equal to, and here we go, N1 minus 1 times the variance here plus N2 minus 1 times the variance for 2, and that's equal to 355.667. And then the denominator is pretty straightforward. Actually, it's N1, which is 12, plus N2 minus 2 gives us 22. And now to get the pooled variance estimator, we simply go equal that 355.6667 and divide it by 22, and it gives us the pooled variance estimator of 16.167. So we're going to use that, like I said again, down here in the calculation for the t-statistic. So let's calculate the numerator here first, which is simply going to be, and I'm going to go up here in the corner and do a split screen. So I click up there and drag this down, and now what I can do is move this around a little bit so you can see some things higher up, which will make it a little easier to show this. So equals x bar 1 minus x bar 2 And since we believe that those basically the hypothesis that there's no difference between the population means that it's going to be equal to 0. At least that's the hypothesis we're using. So minus 0, which is going to give us 1.83333. So that's the numerator. Now the denominator is going to be equal to, and we're going to go square root, and then open parentheses, and we're going to see here, we're going to multiply it by this pooled variance estimator, the S sub p squared, times 1 minus, and you can remember here that the n1 and the n2 are 12, so 12 plus 1 divided by 12, close, and that should, there we go, 1.641476, and now we simply need to do is take the numerator divided by the denominator, which gives us a t-test of 1.12, and now you can see since the t-test of 1.12 is not in the rejection range, because it's not less than negative 1.973 or greater than 1.93, there's not enough evidence to infer that the speeds differ. And I guess what I should have done in the sample, I lost it, is the t that I didn't calculate, so you could see that actually. And just 1 second. Alright, I'm back. I realized on that rejection range that I had a little issue there that I'm going to correct right now. So we have a t-score plus the alpha divided by 2 with v for degrees of freedom, and I'm just going to highlight those, go up here to font, put that down to subscript, make it a little bigger, come back here, equal sign, and I'm going to have to take the sub off there. And in this case it's going to be t in, and I'm going to go 0.025, and the degrees of freedom is going to be 12 plus 12 minus 2, which is the 22, is equal to minus 2.037. I'm going to do the same thing over here, but I'm going to do it on the positive, the t in, but I'm going to go 1 minus 0.025 with that 22 degrees freedom. And so back up here it should really be minus 2.073 or greater than 2.073, and you can see that the 1.12 is not in that rejection range, so there's not enough evidence to infer that the speeds differ. Alright, I hope that was helpful.